Hello and welcome to the WUIVIEW video series. I am Pascal. I'm a PhD student at the Polytechnic University of Catalonia, and I will be talking about the hazards associated with non-natural fuels. Non-natural fuels are those artificial fuels which are present within a property's limits, such as stored materials, outdoor furniture, garden sheds, LPG tanks, vehicles. Some examples can be seen in these pictures. All these are combustible materials which can pose a serious hazard onto structures should they be ignited by an incoming fire front. Their burning time is typically longer than the one of natural fuels, which are present on the property, for example, ornamental vegetation. And thus they expose structures to a fire for a prolonged time. Critical scenarios involving non-natural fuels have been identified from past fires at the wildland-urban interface. These include, for example, the presence of LPG tanks, which, if they are exposed to great heat loads, could release their contents, creating a jet fire or a levee. Another critical scenario includes the accumulation of objects in semi-confined spaces located close to a house, for example, as can be seen in the first picture in the video. If these objects are ignited, they can cause large heat accumulations, which could potentially damage the structural elements of a house. Fuel packs in general, if they are ignited, can release great amounts of energy, which can then impact the elements located in their surroundings. So may this be a house or a LPG tank or other combustible materials, which can be ignited and thus creating a fire spread through the property. It is important to characterize these fuels in order to quantify the hazards that they can pose. Quantitative information regarding their burning behavior is thus needed. The analysis of past fires has led to the identification of pattern scenarios involving artificial fuels, such as those previously described. There is a need for quantitative information on the fire behavior of artificial fuels in order to analyze these pattern scenarios. This information can be found either in the literature on real scale tests or by performing new real scale tests. The information needed for the analysis includes the heat release rate curve of the burning fuels, which is the rate at which fire releases energy. Here is an example of a heat release rate curve of a stack of pallets of 0.9 meters high. The heat release rate will increase over time until it reaches its peak point, its peak value, and will then decay. As can be seen from the graph, the combustion of these pallets lasts for almost 12 minutes and reaches a peak of just above 5 megawatts. Other needed information are, for example, the critical heat flux or the critical temperature of an item, which can give information on when an item that is exposed to a fire will ignite. For example, a person can be exposed to 1 kilowatts per square meter for an indefinite amount of time without feeling any pain. However, if we go up to 6.4 kilowatts per square meter, a person will feel pain after 8 seconds, and after 3 seconds if they are exposed to 10.4 kilowatt per square meter. We have calculated the radiative heat flux of this stack of pallets at the different distances. And as you can see, even at a distance of 3 meters, the heat flux is 7 kilowatts per square meter. So a person would not be able to stand at that distance without feeling pain. So these radiative heat fluxes are actually quite high. When there is no real scale available data on the heat release rate of items or fuel packs, it is also possible to estimate the heat release rate empirically. For example, if you have the area of the fire, the burning rate per unit area of the material, and its effective heat of combustion. However, this information is not always available, and the effective heat of combustion is not constant, and the equation does not take into account the initial transient period. Also, objects can contain different materials. For example, if you see here in the picture, we have a table and chairs which are made out of plastic, but then we have the cushions which are made out of foam and textile materials. So it is really best to have real scale, real test data for the analysis. So taking into account the formula for the empirical estimation of the heat release rate, we have tried to estimate the heat release rate of this fuel pack in the picture, composed out of 4 foam mats, 3 pallets, 6 paint buckets, and 10 cardboard sheets. In the literature, information was found on cardboard, on pallets, and on foam mats. So the peak heat release rate was estimated with the previously shown formula. However, there was no information on the paint. So it's not possible to accurately estimate the heat release rate of this fuel pack. Also, when it comes to the curve, when will this fuel pack reach its peak heat release rate? Will all the items ignite at the same time? Will there be separate ignition? You can see that the curve varies depending on these two criteria. So it is very important to find accurate information on the heat release rate curve of the items that can be present on wetland urban interface properties. So now, how do we actually measure the hazard that is created by the combustion of these items? For the analysis of different fire scenarios, fire practitioners use computational fluid dynamic tools, which numerically solve the conservation equations of mass, energy, and momentum to represent the fluid flow. The tool that we are using is FDS, is the Fire Dynamic Simulator, which is a CFD model of fire-driven fluid flow and puts emphasis on smoke and heat transport from fires. It is used to calculate the effect of flame impingement and heat exposure on structures and on people, and it can be used as well for fires that are coming from the outside towards a structure or fires inside a structure. It is used for the performance-based design approach for the vulnerability assessment of buildings. For FDS, the inputs that are needed to simulate a fire in a domain are the geometry of the fire, so the area of the fire, and its heat release rate. For example, you can insert the heat release rate curve of the stack of pallets, and also the geometry of the dwelling and of the environment that you want to simulate, along with the environmental characteristics. The outputs that you can get are, for example, the heat fluxes at certain distances from the fire. You can see here a heat flux curve from the fire, and temperature profiles. For example, here you can see a figure with a slice file of the temperature of the fire. For the purpose of these simulations, a database has been created, which is accessible through the WUIVIEW portal, which contains quantitative information on real-scale non-natural fuel hazards that can be used as input for the simulation, so as input for a fire scenario. This is a dynamic database, meaning that we are constantly updating the items that are present, so adding new information once it comes out. And we have quite a few categories at the moment. So there is information on furniture, on appliances, on decoration. At the moment, we have 46 items in this database. An example of what type of information it contains is here given in the picture here. So we have data on the geometry of the item, on the heat release rate, on the mass loss rate, fire growth rate, spread rate, critical heat flux for ignition, along with all properties such as the heat of combustion of volatiles. So any information that can be found in the literature about an item is actually collected in here. Here is an example of an object, which is a wood pallet. And we also have different heat release rate curves depending on the height of the stack of the pallets, as can be seen here in the list. We have a stack of, for example, 2.4 meters down to 0.9 meters. And so by clicking on these items, you actually get an Excel spreadsheet with the heat release rate curve of the item. And again, here is an example of our stack of pallets of 0.9 meters. So to conclude, we have seen that the hazard of non-natural fuels is actually often disregarded, even though the burning time of these items is generally longer compared to natural fuels. Quantitative information is needed for the estimation of the hazards that they create. And for this reason, we have created a database with all this information, which can then be used as an input for the analysis of scenarios with the aid of CFD tools such as FDS. Well, thank you very much for watching.